first video, we introduced the Galois correspondence, and now we want to talk about some properties of the Galois correspondence. So this is all part of the fundamental theorem of Galois theory. So I'll write fundamental theorem continued. And we'll prove a few things. Under this correspondence, what happens? So first, this correspondence is inclusion reversing. So if you have two subfields of K containing F, E1 and E2, and they correspond to two subgroups of G, H1 and H2, then E1 is contained in E2 if and only if H2 is a subgroup of H1, if H2 is contained in H1. And this is proposition 4 that we proved several lectures ago. So we've already done this proof when we were first talking about fixed fields of subgroups of groups of automorphisms and groups of automorphisms that fix a particular field. Okay, so there's nothing left to do there. We know that this correspondence is inclusion reversing. All right, so next let's talk about sizes of subgroups and degrees of field extensions. So let's suppose that E is the fixed field of H for some subgroup H of G. So we know now that every subgroup of K, every subfield of K containing F is the fixed field of H for some subgroup H of G. How big is H? The order of this group H is the degree of K over E. And what about the degree of E over F? The degree of E over F is the index of H in G. Okay, so I wrote this because we're now using the same notation for different things, right? So this notation here, this is the degree of the field extension E over F. And here, it's the index of a subgroup, the index of H in G. Okay, so I drew this little diagram because I find it helpful. We have K, E, F. And then on the other side, we have the trivial subgroup, the whole Galois group. And in the middle, we have H. And these correspond to each other under this Galois correspondence because E is the fixed field of H. Okay, so the proof follows pretty directly from Theorem 9. So Theorem 9 says, okay, E is the fixed field of a finite subgroup of automorphisms of our field K. So what is the degree of K over E? It is the order of that group. So Theorem 9 gives us the first statement directly. So now we know what is F. F is the fixed field of ought K over F, right? So because K over F is Galois extension, this is true. This is the fixed field of the whole group G. So Theorem 9, okay, also says that the degree of K over F is the order of G. This also just follows directly from the fact that we know K over F is a Galois extension. Okay, but now we can use these two facts together. We also know what is the degree of K over F by this multiplicative law for degrees of field extensions, this Tower law. The degree of K over F is the product of the degree of K over E times the degree of E over F. But the first of these degrees we know is the order of this subgroup H. So what does that mean? This is the order of G. This is the order of H. So if we just divide, we see that the degree of E over F is the order of G divided by the order of H. These are finite groups. The quotient of, the order of G divided by the order of H is the index of H in G. All right, so I'll pause and erase, and then we'll see how this piece, this property of the correspondence, tells us something interesting in examples that we've already looked at. Let's go back to this finite field example. Fp to the n is a Galois extension of Fp, and the Galois group is isomorphic to Z mod nz. We know everything we could possibly want to know about subgroups of Z mod nz. there's exactly one subgroup of order D for each D dividing N. So let's say D divides N, and let H be that unique subgroup of Z mod NZ of order D. And now let's take the fixed field of H. Let's call that E. So what do we know? This property that we just proved says that the degree of Fp to the N over E is D, and the degree of E over Fp is N over D. So what does that mean? So E is a finite field of order P to the N over D. It's an N over D dimensional vector space over Fp. So this is how many elements it has. All finite fields of given order are isomorphic to each other. It's isomorphic to Fp to the N over D. Okay, so what are we seeing? For concreteness, I mean, if we know that this Galois group is generated by this element, sigma p. So what is one way to think about what is this unique subgroup of order D? It's the one generated by sigma p to the N over D. So here's our subgroup diagram. What happens over on the subfield side? Fp to the N, Fp at the bottom. We have this fixed field of this subgroup, and we know the degrees in this tower. It has degree N over D as a field extension of Fp, and Fp to the N has degree D over E. So what are we seeing? If we know the size of this H, so for each subgroup H of the Galois group, we get a subfield over here, and all of the subfields come from subgroups in this way. This correspondence from subgroups to subfields is surjective. And if you know the order of the subgroup, that determines the degree of the subfield as an extension of Fp. So for each subgroup, we're getting a subfield of a different order. So that means for each D dividing N, there is a unique subfield of Fp to the N of order P to the N over D. Okay, so this is something that we'll come back to and talk about a little more when we talk about section 14.3, but we're seeing that the properties of the Galois correspondence already are helping us to understand things that we didn't know before about subfields of fields like Fp to the N. Okay, so I'll pause and erase and then talk about some other things you might want to know about the Galois correspondence. Let's talk about our next property of the Galois correspondence. Let's say that E is a subfield of K containing F. It's the fixed field of some subgroup H of G. So let's say that E is the fixed field of H. K over E is always a Galois extension, and the Galois group of K over E is isomorphic to H. And this is something that we've pretty much proven already. This follows immediately from corollary 11, which says you have some finite subgroup of the group of automorphisms of a field, and you take its fixed field, and your field K is a Galois extension of that fixed field with Galois group isomorphic to your subgroup. Okay, so there's nothing to prove here. So now what I want to do is look at another one of the examples that we've talked about already. Let's take this field generated by cube root of 2 and zeta of 3 over Q. So K is this field, F will be Q. We know the Galois group of K over F, we found two particular automorphisms, sigma and tau, that we talked about in an earlier lecture, and saw that this is an extension of degree 6. Sigma and tau give two automorphisms, and the group that they generate has order 6. It's not abelian, it's isomorphic to S3. So sigma cubed equals 1, tau squared equals 1. And we looked very explicitly at these automorphisms and how they act on elements of this field. Okay, so we have this Galois group. We can look at its subgroups. We have the identity up here, the one generated by sigma, the one generated by tau sigma, by tau sigma squared. And we have the whole group at the bottom. And for each one of these subgroups, we can take its fixed field. And you can check that these are the fixed fields. And now, given the Galois correspondence and what we know so far, we know that there are no other subfields of K containing Q, that these subfields are the only ones in this diagram. So we have like Q adjoin zeta 3, Q adjoin each one of the 3 roots of x cubed minus 2 in K. That, for example, the field generated over Q by cube root of 2 doesn't contain either of the other 2 roots. These 3 fields are distinct, but are isomorphic to each other. OK, so what is this third property telling us? We know that K over E is a Galois extension for each subfield E of K containing F. So each one of these extensions is Galois. For example, K is a Galois extension of Q adjoin zeta 3 times cube root of 2. OK, but what about extensions of Q? We know that K over E is Galois. And the question we want to understand next is which E over F are Galois extensions? So in this case, which extensions of Q in this diagram are Galois extensions of Q? And we know that Q adjoin zeta of 3 is a Galois extension of Q. Why? It's a quadratic extension of Q. It's a quadratic extension of a field of characteristic 0. This is Q adjoin square root of negative 3. So this one is Galois. But Q adjoin cube root of 2 is not a Galois extension of Q. For one thing, it's just not the case that every polynomial in Q bracket x, which has a root in Q adjoin cube root of 2, has all of its roots in Q adjoin cube root of 2. For example, x cubed minus 2 has 1 root in this extension, but it does not have 3 roots in this extension. OK, so in the next video, we'll use the Galois correspondence to understand which extensions E over F are Galois extensions.